Hey everybody, this video lesson is going to talk about something called redox reactions. Redox reactions are defined as a chemical reaction in which an electron is transferred from one substance to another in the process of the reaction. Anytime an electron gets transferred in a reaction, it is the characteristic of a redox reaction. Now, in the process of the electron transfer, the resulting compound or element may be an ion, but it could go from an ion to a neutral state. But this little note here is just here to remind you that an ion may be the result of a redox reaction. It doesn't always have to form a neutral compound. Now, in previous chemistry classes, we probably learned about different types of chemical reactions. At least in my experience of teaching, we learned about synthesis, decomposition, single displacement, double displacement, and combustion, the 5 types of chemical reactions. But in AP chemistry, we actually lump many of those into one group known as redox. Synthesis, decomp, and single displacement are all considered redox reactions because they all involve the exchange of electrons. Double displacement, or precipitation reactions, is kind of in a category all on its own, and combustion reactions are also a form of redox. Now, what does redox really mean? The word redox is really made up of 2 words, reduction and oxidation. Oxidation is when an element or ion increases its oxidation state or loses electrons, whereas reduction is a situation where an element or ion decreases its oxidation state or gains electrons. Another way of thinking about oxidation is that the ion or element becomes more positive. Metals tend to want to lose their electrons and become more positive, so oftentimes you'll see metals oxidize. And because of the opposite effect, nonmetals like to gain electrons, and they're more likely to become reduced. Reduction, decreasing the oxidation state, can be reworded as saying becomes more negative. I drew a number line up in the upper right-hand corner to try and illustrate this point. Oxidation becomes more positive because the element loses its electrons, and you subtract a negative charge, you become more positive. So oxidation is a situation where the element or ion becomes more positive. Now, you could start out as positive and become more positive, and that's still oxidation. Whereas reduction, on the other hand, would be a situation where you're gaining electrons, and so you are becoming more negative or less positive. So if you think about the number line, if you move to the right, starting at 0 or +1 and becoming more positive, you're oxidation, and at 0 or -1 or -2 become more negative, you're being reduced. Now, when you look at a chemical reaction as it lies there on the page, sometimes it's pretty difficult to figure out which substance gets oxidized and which substance gets reduced. But there's always coming in companionship with one another, meaning that the oxidation always results in a reduction somewhere else in the reaction. You'll never have just oxidation alone or reduction alone. They come kind of coupled together as a pair. And in order to figure out what gets oxidized and what gets reduced, you oftentimes have to identify what are referred to as the oxidation states or oxidation numbers. Now, here are the rules for assigning oxidation states or oxidation numbers. We talked about this a couple slides ago, but we need to identify each element in the reaction to determine if it's going to oxidize or reduce. But before we do that, we need to figure out what its oxidation state is so that we can observe the change, either loss or gain, of electrons. Now, page 132 in our textbook has the wordy version of these rules, but this is a summary of them. First rule is that oxidation states of any element or diatomic is always 0. So if it's off the periodic table or it's a diatomic like O2 or N2, there's simply 0 oxidation state. Now, the second rule, oxidation state, for any monoatomic ion is equal to the charge of the ion. Now, this is where a chemistry teacher or chemistry professor might get a little nitpicky about the order in which you write the charge or oxidation number for a particular ion. Technically, if you're going to assign a charge to an ion, you put the number with a sign after it. So the ionic symbol for sodium is 1+, but its oxidation state is +1. So if you see the number first with a charge after, that's a charge, but the oxidation state is equal to the ionic charge. It's just the reverse order. Now, I personally am not going to get too nitpicky about this, but you may come across a teacher, professor in your future studies that does, so just know the difference. So going back to rule number 2, if you recognize that a substance is ionic and you know the charge of those ions, you simply know that the oxidation state is the charge of the ion. Now, these first 2 rules kind of apply to a large group of elements, But 3, 4, and 5 are going to apply to specific elements. And these specific elements are going to be more helpful when trying to determine the oxidation status of other elements that you may not know the oxidation states of right offhand. Rule number 3 says oxygen is -2 when it's in covalent compounds, with one exception. Peroxides are -1. Now, oxygen's -2 always when it's in an ionic substance, but when it's in a covalent substance, it's also -2. Peroxides, or the polyatomic ion O2 -2, each oxygen has a -1 oxidation state. Next, rule 4, hydrogen is +1 in a covalent compound. Now, like before, it's +1 in an ionic substance when it's listed first, like hydrogen chloride. Any acid, the hydrogen is +1 oxidation state. But in covalent compounds, it's also +1. The only times it would be -1 is if it came second in an ionic compound. For example, CaH2, calcium hydride. In that case, each hydrogen would be a -1 oxidation state. And finally, the fluorine is always a -1 oxidation state. The other halogens could have other oxidation states or oxidation number possibilities, but fluorine is -1 and always -1. I'd like to quick add in a 6th rule, if you wouldn't mind, and it pertains particularly to halogens. Halogens, when they're on the outside of a compound, meaning the ligand, if they're not the central atom, but if they're on the outside, they're also -1 in compounds. But they may change if you have them on as the central atom. So halogens are -1 in compounds as long as they're on the outside of the compound. Other than that, these rules are pretty much all you need to know in order to do the following practice problems. Now, before we get to actually assigning oxidation numbers or oxidation states, the last 2 guidelines that I want to point out to you are these: that in a compound, you add up the oxidation numbers, they should always equal the charge of the molecule. So if the molecule is neutral, then the oxidation numbers should cancel each other out. If the compound is a polyatomic ion, then the oxidation numbers should add up to equal the charge of that polyatomic ion. Second, in a reaction, the charges or the oxidation numbers have to equal on the reactant side and the products. You don't have to have eliminated the oxidation numbers on the reactant side. It doesn't have to add up to be 0 overall on the reactant side. It just has to be equal to the oxidation numbers added up on the product side as well. Again, that goes back to the law of conservation of matter and the law of conservation of charge in this case. So next we're going to do some examples. What are the following oxidation states for each element of the following? So what you do is you look at each individual element in these examples down below. Keeping in mind our rules, we can assign oxidation numbers to each element in these compounds. Let's first start with SO2. So I know from my previous rules that oxygen is always a -2. So if I rewrite this out here, each oxygen is a -2. Now there are 2 of them, so overall there's a -4. Now because this molecule is neutral, I know that the oxidation numbers have to add up to be 0. Now if I have 2 oxygens, both at -2, then that must mean that the sulfur is a +4. So if I assign oxidation numbers to sulfur is a +4, and each oxygen is a -2. Now the next one is PCl5. Rule 6 from last slide mentioned that any halogen on the outside is always a -1, so there are 5 of those. Chlorine is going to be on the outside with phosphorus in the middle. Now chlorine on the outside is going to act like most halogens on the outside, and those are all going to carry a -1 charge. In fact, most halogens have a -1 charge. Fluorine's always -1, but the other ones may be something other than -1 if they are on the inside or the central atom of a molecule, for example, the chlorate polyatomic ion. But this chlorine, each one is on the outside, and each carries a -1 charge, or a -1 oxidation number. Since there's 5 of them, that means that this phosphorus must be a +5 oxidation state. Finally, chlorate, as I had just mentioned, is a polyatomic ion, ClO3-1. Now, I know that in the end, all of my oxidation numbers have to add up to equal a -1 charge. So we need to figure out the oxidation numbers for each of these elements. As we mentioned before, oxygen is always -2. And there are 3 of them, so overall I have a -6. Now that chlorine has to add up so that in the end a -1 is left over. So that must mean that the chlorine acts as a +5 oxidation state. So you can see in 2 different examples, chlorine is acting as a -1 in this example when it's an outside element or a ligand. When it's the central element, it changes its oxidation number altogether. So, in summary, the oxidation states for the different elements depend on how they're combined with the other elements. You usually can figure out one of the elements pretty easily or pretty clearly, and then using subtraction or basic arithmetic add up so that you can figure out the unknown identity of that central atom usually. In sulfur's case, +4, in phosphorus's case, +5, and in chlorine's case, +5. Now let's apply this to whole chemical reactions. This first example says assign oxidation numbers to each element the following reaction. Identify what gets oxidized and what gets reduced. Now I can't identify what gets oxidized and what gets reduced until I establish the oxidation numbers. So I'm going to begin by just simply grabbing a pencil and starting jotting down what I know. So for example, I know oxygen here is a -2, and this is ionic because it's combined with iron, and there are 3 oxygens, so that must mean each iron is a +3 charge, or +3 oxidation state, I should mention. Now the next reactant is carbon, and this is carbon in its elemental state, so it has a 0 oxidation state, or a 0 oxidation number. Now on the product side, you find iron, iron being in its elemental state, not combined with anything, so that is 0. Oxygen in CO2 is always -2, and there is 2 of them, so that must mean the carbon is a +4. Now I have the oxidation numbers assigned to each element, and I can see that on the left I have 3, -2, and 0, and on the right I have 0, +2, and -2. So next I have to figure out which element gets oxidized, meaning it goes from a low oxidation state to a higher oxidation state. And in this case, I look at carbon. On the left, it has a 0, and it ends up as a +4, so it becomes more positive. It loses electrons. Oxidation is a loss of electrons, increasing its oxidation state. So what gets oxidized is carbon. Now what gets reduced, I need to figure out an element that starts out at a high oxidation state and reduces or goes to a lower oxidation state. Now oxygen starts out as a -2 and ends as a -2, so it's not actually oxidizing or reducing. But the other one that I haven't mentioned yet is iron. It starts out as a +3 and goes down to a 0. So what gets reduced is iron. Now this problem isn't balanced. You can see you have an unbalanced chemical reaction with 2 irons on the left and only 1 iron on the right, and you have 2 oxygens left, but right, and 3 oxygens left. So it's not balanced. But it doesn't ask you to write the chemical reaction balance. It just asks you to identify the oxidation numbers and figure out what gets oxidized and what gets reduced. And you don't need to have a balanced reaction in order to figure out what gets oxidized and what gets reduced, because oxidation numbers are for individual elements only, not for the overall reactant or overall product. But I do know that the oxidation numbers in this neutral molecule add up to be 0, and the same as with this one. But the oxidation numbers for the overall reaction don't necessarily add up to be 0 right now because it's not a balanced chemical reaction. Now let's take a look at the second example. It says predict the products, then assign oxidation numbers, and then tell me what gets oxidized and what gets reduced. So I take a look and I see a single metal and a metal ion, and this looks like a single displacement reaction. And we'll talk about predicting products here in the next video lesson. But cadmium comes in and kicks out tin, so tin is by itself, and now cadmium is with chlorine. And cadmium is just below zinc on the periodic table. And I know zinc is a +2 charge, so I'm just going to pick a oxidation state for cadmium. I'm just going to say it's a +2 charge, which means that there's going to be 2 chlorines, each of which are -1. Now let's go back to the original reactants and figure out what the oxidation states are for those. Before I do that, I can actually finish off the products, because tin's in its elemental state, so it's 0. Now let's go back to this side, the reactant side, and figure out. Cadmium starts out as a 0 because it's in its elemental form. Chlorine is a -1 because any halogen outside on the ligand is a -1 charge or -1 oxidation state. And then tin must be a +2 charge or a +2 oxidation state because the way it's combined with chlorine. Now I can identify something that goes from 0 and turns to a +2. That means it gets oxidized. Or in other words, it turns into an ion. If a metal becomes an ion, it gets oxidized. If a non-metal becomes an ion, it gets reduced. So, a metal that gets turned to an ion is oxidized. So in this case, cadmium gets oxidized. What gets reduced then must be the tin. It goes from a +2 charge down to a 0. The chlorine keeps its oxidation state in both cases. Now redox reactions, like any reactions, have to be balanced. And in AP chemistry, we use the net ionic reactions. to represent the redox, because you don't really care about the spectators. The spectator ion is in the beginning and at the end of a reaction and simply just cancels out. Another characteristic of spectator ions is that they don't get oxidized or reduced. They keep their charge either +1 or +2 on the reactant side, and they're also +1 and +2 on the product side. And we'll illustrate this in an upcoming example. But spectator ions keep their charge and state of matter, whereas something that gets oxidized or reduced changes its charge and might change its state of matter also. In a redox reaction, we also must balance the electrons lost or gained. If 2 electrons are lost, then 2 electrons must be gained as well. Because the law of conservation of matter exists, electrons must be lost and gained equally. And finally, a simple note, redox reactions tend to balance themselves. And what I mean by that is that the electrons will balance out when you balance the atoms in the reaction. You don't have to worry about messing around with any of the electrons on either side, because they're just going to kind of work themselves out at the end. Now, these redox reactions are simple redox reactions. We're going to stick to those simple types here in this chapter, but later on in this curriculum, in the 3rd trimester, we're going to talk about balancing redox reactions that aren't so simple. So that's a little foreshadowing. Now let's use the example from the last slide. It was the Fe2O3 plus carbon example. And those two reactants combine together to create iron and carbon dioxide. And just to remind you, I wrote the oxidation numbers in red. So now let's balance this chemical reaction. Now this reaction is already in its net ionic form, because let's just assume that this is aqueous, that this iron oxide is aqueous, but iron starts out as aqueous and turns to solid, and then carbon starts out as solid and turns to gas. So none of these substances start out as aqueous and end as aqueous, so this is the net ionic reaction. Now I need to balance the elements on each side, and I could start with the iron or the carbon, but the carbon is already balanced, so actually I'm going to start with the oxygen. I've got 3 oxygens on the left and only 2 on the right, and so I'm going to double this to figure out that there are 6 total oxygens now on the left, and I'm going to multiply this to make it 6 oxygens on the right. I come back and balance my carbon. There are 3 carbons on the right, so I'm going to do 3 carbons on the left, and finally finish with my irons. I've got 2 times 2, or 4 irons on the left, so I have 4 irons on the right. Now just to show that the electrons balance themselves, let's take a look at the irons, shall we? We've got 2 times 2, or 4 irons, and each one of those irons is a +3 charge. So overall, we have a +12 on this side in terms of oxidation state. Now, because the balancing must occur, we must also have a +12 gained on the product side. What gets reduced, or what gains, is the carbon goes from a 0 to a +4. So we need to have a +12 accounted for on the product side as well of what gets gained, or electrons. So these 4 irons here lose 12 electrons total. Now those 12 electrons need to get picked up by something else on the product side. And if you look, we have 3 total carbons, because we got 3 CO2s, so 3 carbons, and each carbon is a +4. That means that 3 times +4 is a +12 on this side. So we've got 12 electrons lost by the iron was picked up by the carbon, and the carbon went from a 0 to a +4, or in total picked up all 12 electrons to become a change or reduction of +12. And that's what I mean when I say simple redox reactions balance themselves. Anyway, that takes care of this video lesson. Thanks for watching.